Okay, hello everyone. My name is Filipp Keks. I will talk today about mobile graphics, mostly about programming GPU and why it is so hard. I will talk about why there are not so many games or some graphic intensive applications for mobile devices which look good. This is actually quite a mystery for me. It was before I figured out why, and now I share my experience. I want to know you a little bit more. Who of you already had some experience programming graphics, GPU programming, right? Writing shaders. Okay, some people, cool, and others don't know much about it. Okay, so I will try to please all of you. I will try to please the guys who already know something, to give some new information, and also try to explain some very basic stuff for the guys who don't understand anything at all. I will talk a little bit about myself. For about first 10 years of my professional experience as a developer, I was working as in the enterprise software, mostly Java and Oracle, hardcore stuff. Actually, I was working for the Swedbank. I saw you have like a big Swedbank building right here. And now, like 4 years ago, actually, I switched totally the fields. I went to game development. I actually thought it would be much more similar in the beginning to my experience in the banking software. In the end, it came out that it's a little bit different. I will explain why a little bit later. The biggest problem, of course, yeah, the graphics. Graphics is different. I will start from stating the problem, probably, from this slide. Maybe you already know that modern mobile phones, they are comparable by their specs to modern consoles and PC hardware. For example, this device, I have iPhone 6s. It has a hardware like GPU and CPU almost the same as PlayStation 3 has. The question is, why when you see the PlayStation 3 games and you check out the mobile phone games, they still look like mobile phone games? The graphics is not on the same level. Have you ever thought about it? And actually the mobile device companies who make mobile phones, they advertise their phones as they are on the same level as the gaming hardware consoles, but you never see games on the same level. There are several reasons. I will, during all my presentation, I'll explain all of them and propose how to fix them, for example. But I will start probably for the guys who don't understand anything about how the graphics programming going on. I will do a little bit of coding demo. Okay. Mostly in my work time, I use Unity for programming. Actually, I thought about using WebGL for this presentation, but I thought it will take me a little bit more time than I'm using Unity. I hope you guys know what Unity is, right? Like a gaming engine, which helps to a little bit speed up the development of the games. So we have a sphere here, which looks like a ball, which is rendered by GPU. And I will show how it is rendered. I wrote a small shader, like a stub. I'll zoom it in. So, GPU is a separate processing unit inside your computer or mobile phone, which works in parallel with CPU. Probably you already know. But it works a little bit different. It's only it doesn't have jumps in it. For example, if you check out your CPU assembler code, if you make an if statement in the code, actually inside in the bytecode machine code, they have like jumps. And the GPU is different, it doesn't have jumps. It must execute everything what it has in the bytecode. It gives some advantage, it gives a big advantage that you can execute a lot of parallel threads of the code without fearing that some like inconsistencies will happen because of the jumps. But at the same time, it gives a little bit of problems for the developers. So the usual shader code, we have basically two functions here. One function is executed to every vertex of the sphere I have shown you here. I will show how the vertices look like. Probably like this, yeah. So each dot is of sphere is a vertex where the lines come together. So first, the GPU executes this function for each vertex. It takes the position of the vertex from the sphere model and then projects it to the screen, to the 2D screen. And the fragment shader, the second function, it just returns the color of the dot. So currently it's returning 1, which means white, so the whole sphere is just white, easy. Like if I turn it 0, then it's black. So what can we do with it? We can play with it around. For example, I can take from the model of the sphere, which was probably made in some, I don't know, some other software, like, you know, 3D Studio Max or something like this. I can take some other parameters, not only the positions of the vertices. For example, I can take the normal. You guys know what is normal. Yeah. If you have some surface, so the normal goes to in perpendicular to the surface. So if I take a normal, I take a normal of a vertex and pass it from the vertex shader to the fragment shader. And I'm using this special structure to pass data from 1 to second. And actually, this data will get interpolated when the triangle will be drawn on the screen. So if I pass a normal to a fragment shader and display it as a color, what do you think? What will sphere will look like? Something, typo, normal. So, what color the sphere will be? If you know what is normal, it is somewhere directed to the x-axis, y and z-axis in the sphere, all directions. Any proposal? Which color? Black. Okay, let's check it out. And why is that? Because we have RGB colors in the same exact order, and we have x, y, and z axis. So R goes to x, G goes to y, and so on. So the green is y axis. That's why we have green up. It's because the y axis goes up. Blue is z, and so on. You understand the idea. I don't know. We can play a little bit more with it. For example, we can change the positions of the vertices. We can not only change the colors of the points, so we can change the position in the vertex purely using GPU code, not using CPU at all. For example, I want vertices to change their positions randomly. There is a problem. There is no random function in the GPU, so I have to write it by myself. But there is like a standard way to do this. It looks something like this. So I have a random seed, and some graphics magic goes here. Seed. I have to do it a float. Just some random numbers to make it look more noisy. And let's take a fraction of this one. You guys know how the random algorithm actually works in real life. This something is similar. And if I add this one, normal, something like that. Oops, error. Yep, here. Still. Ding, 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 ding. 1 second. Yeah. Yep. So what we have here, we have the same sphere, but I use normal of each vertex of the sphere and added like each dot went to the direction of a normal, but with random distance. So as you can see, we have some kind of like a bubbling wobble. And now, I don't know, I can animate it, for example. I actually have like some ready to go copy-paste code here, so we don't have to wait. Probably will be easier. Jump. And when I go execute this, so the only thing which is passed from the CPU to GPU is the time, as a float, one number, and everything else is done by GPU. So it's purely GPU code. We can experiment with it. Do a lot of things. Add some colors, do some psychedelic special effects. If you didn't play it with this thing at home, I think you have to do it. And I can show an example, for example, what can be done with purely GPU code. Maximize. Oh, wrong window, sorry. So this effect okay, never mind, I will not maximize. Super. So this scene is drawn purely with GPU code, and all the geometries you see there is purely done with functions. There are no like pre-built geometry from anywhere before, and it's purely calculated by GPU, and all the reflections. The resolution here is quite low. I did it especially for the purpose it will like work faster, because this one use ray tracing. And the sphere which is flying there, it has actual like the real-time reflections, which are ray traced from the environment. And this is done real-time, but it eats quite a lot of GPU resources, like 100% of GPU resources. Just to make an example, show an example what can be done with GPU. And actually, I have the same demo running here on the phone also. Yep. And I will show you a little bit more about this demo a little bit later. So, now that you know a little bit of how GPU works, so I'll tell a little bit of history, how it became to be. So the first graphic accelerators, they were not named GPU before. First graphic accelerators appeared in the arcade machines somewhere in the 70s. But they were purely like 2D accelerators, probably for rendering sprites on the arcade machines, because CPUs were not powerful enough to display so many pixels at the same time. And in the 90s, actually, in the 90s appeared first commercial graphic accelerating cards which you could buy. They were absolutely proprietary. Voodoo was the name of the cards. I don't remember what's the company name. And they had...
3DFX.
Which one?
3DFX.
3DFX. Okay, probably you had one at home.
Yeah.
I had one at home too. I played Need for Speed, I think. With my first.
Unreal Tournament first version.
First version. Yeah.
They looked better than on OpenGL cards of that era.
Yeah, these were mainstream, and actually they were, for that time, quite good quality. One problem they had, this Glide API which we used was absolutely proprietary, and if you made a game for the Voodoo card, it will never work with any other card, because no other card could replicate the same API. It was not opened. And somewhere later, also in the 90s, appeared new standards for API. OpenGL was like an open API, and of course API wars started at that point, so Microsoft invented their own DirectX API, which was quite similar in the beginning, and then they started to become more different. And the term GPU, which we use widely right now, like graphic processing unit, it was invented by NVIDIA, and they had actually quite a war of terminology, like ATI. They produced their cards and they advertised them as VPUs, like visual processing units, and NVIDIA, they forced the GPU, and so in the end, NVIDIA name stuck, so we now use GPU name. And somewhere later, 2005, probably a little bit earlier, maybe 2003, first OpenGL ES appeared. OpenGL ES is a standard API for the embedded devices. It's called OpenGL, like for embedded devices. And this is what we use now in our phones. Actually, in the most phones, and in WebGL, also based on the OpenGL ES. And OpenGL ES second version is currently the most widely used API, graphic API in the world. Like if you compare by number of devices. And the popularity is exponentially bigger than any other API. WebGL, the graphics API which is used for the web applications, also appeared, 2011. Also OpenGL 2 based, and actually WebGL 2 appeared recently, and it's OpenGL 3 based. And if you heard, like a little bit later, 2016, last year actually, was announced a new generation of graphic APIs, and the main one is called Vulkan. Have you heard about it? No, nobody. Okay, one person, cool. And of course, 2017, it's our meetup also, point of history. Oops, little bit pictures went repositioned. Okay, never mind. So I named my presentation the horror of mobile graphics. So why it is a horror? Why it is so hard to make mobile graphics? The problem is the API. First biggest problem. The API was invented in the 90s, and in the 90s the hardware of the graphical devices were a little bit different, and the API was actually quite hard-coded the structure of the hardware structure of old devices. And new devices, they are not very compatible with old API, but they still try to use it because it's widely spread, and it makes a lot of problems. For example, all old APIs, including OpenGL and OpenGL ES and DirectX, they are global state APIs. It means, what does it mean? It means you cannot use this API in multi-threading. If you have CPU, modern CPUs, they all have multi-cores, but you cannot send commands from CPU to GPU from multiply cores, or at least it's very hard, just because the old school APIs are global. They have global state. Have you ever noticed you're playing a game on your PC, your full GPU is used, all the resources are used, but only one core of the CPU is used. All other cores are resting. Have you ever noticed it? This is just because of this problem. All shaders, the shader code I just wrote in front of you for GPUs are shipped as a pure source code. And there's like, if you start an application on your device, on your PC, the program sends the pure source code without compilation to the driver, and the graphic driver is responsible for compiling the code real time. Maybe in the beginning of the API development it was a good idea, but actually it came out to be a very stupid idea because every graphic driver has its own compiler for the shader code. Even if shader code is the same for all different hardware, if you try to compile the same code by 100 different compilers, of course you have differences. Every compiler has its own bugs, and it makes quite a huge problem. Like, for example, if you have a shader and you have some brackets put somewhere in different position when it usually is, you may guess that 1 in 100 compilers will fail, and these bugs are very hard to find actually. Memory. Historically, the memory of GPU and CPU were separate chipsets, and the API is responsible for constantly copying some data from one chipset to another. For example, if we had the sphere, a number of vertices with their positions, and it's located usually somewhere in the memory of CPU, like loaded from the hard drive, for example. And in some moment to make the sphere to be displayed on the screen, you have to copy from one chip to another one. But actually at least modern mobile devices, they all have memory chips unified. The copying of the data is not needed actually on the mobile devices. But it actually still happens. It copies every time you need to send some data from CPU to GPU. It takes this data, converts it, and places on the same memory chip. And it's actually this thing which is not needed at all currently. But all the graphic applications, they are forced to do this because of the old API. No programmable blending exposed. Blending is a kind of operation. If you have, for example, I will probably better show. Blending happens if you have a transparent shader. For example, this command will make our sphere transparent, hopefully. Yeah. I just made a different blending mode. It means it takes the points on the screen, the pixel on the screen, multiplies it by 1, adds the pixel which was produced by my fragment shader from here, multiplies it by 1, and adds them all together. This is a simple operation, but old API does not allow me to write it as a math function. I would like this to write as a math function, just one parameter multiplied by something plus other parameter, or I want to make a power of one parameter by other parameter. And it actually is possible in the modern GPUs, but just old API does not allow to use it. So this this blend function, as it's written here in shader code, is very limited. But actually, the hardware allows me to do much more, to blend pixels together currently. But I just cannot use it because of API. So, and last one, my points. Old API doesn't state anything about when the driver can do some particular things. For example, it is absolutely normal for old school APIs to recompile all shaders at some point and take a couple of seconds to do this. So you're playing a game, then hop, you have a glitch for 2 seconds, and then playing again. And those glitches, they happen on the level of the driver, and the application cannot do anything about this. This is actually also a very strange thing why they didn't think about this, to exactly state when which point driver can recompile something or copy some buffer to another place or something like this. Not stated in API, so they do it whenever they want. Okay, horror tools of horror. At least for mobile devices, there are good tools for profiling and analyzing the work of the GPUs which are in PCs and in consoles, but there are no good tools for mobile devices. Why? Because each graphical vendor makes its own tools. There are no universal tools which would work with every phone or every GPU. And some tools are very bad. So if some vendor, for example, we have here, I have like 2 variants here. Qualcomm, they make Snapdragon GPUs and Adreno GPUs. They're quite popular ones in Android devices. And they have a tool which crashes every minute when you start it. You just start it, it crashes. When you try to connect it to some phone, it just wouldn't connect, and so on. A lot of problems. Even worse problem, when a vendor, for example, a mobile vendor like Samsung, they buy a GPU from a Qualcomm and put it inside their phone. And they close all the gates made by Qualcomm, so you cannot connect a profile to the phone. And sometimes you have to hack your phone to root your device or to jailbreak your iPhone to get just a way to connect the profiler. And this takes a lot of time of your work. Sometimes you just don't do it. You don't profile. Just okay, some glitch. Okay, users already used to those glitches. Yep. And probably the most fundamental problem of mobile devices. They overheat. PCs don't overheat because they have coolers. The same have the consoles. You cannot put a cooler inside the device. And it's quite a strange problem because it's mostly caused by spec wars. You know what is spec wars? It's like two vendors, 2 mobile producers now, Samsung and HTC. They made 2 similar phones. They put some graphics devices into it, and when user chooses a phone, it just checks the specs. Okay, it says, oh, HTC has some graphic GPU 180 something, and Samsung has 190 something. Oh, I will take 190 something because the number is bigger. But it actually means, what it actually means, that the phone will be bought. The users will better buy the phone with bigger spec, with bigger numbers. But it of course means it will overheat much faster. And when phone overheats, the frame rate drops quite dramatically. And the reality is, if Samsung would put a little bit lower device, a little bit lower chipset into their device, it would work faster because it wouldn't overheat slowly, and it would work faster. But the number will be lower and people wouldn't buy it. For example, lately I have composed Small table. I hope I will get it. This one. Yep. So this is a small table I made like benchmarking by myself, small benchmarking test. It's visible, right? So this is for 4 Samsung phones, Galaxy S4, 5, 6, and 7. And I plan to do for 8, we just had pre-ordered it. And if you see I put here the number of the vertices can be shaded during 20 milliseconds. And you can see that you have 4 and 5, 500,000, 900,000, 200,000, 200,000. What does it mean? It means that these 2 GPUs are much more powerful than these ones, but I tested them and they overheated. And this was the frame rate drop when they overheated. So there is no point. They're the best, so if you want to buy a phone to play mobile games, buy that one, S5, because it's like has better balance. After S5, they made a mistake, and they went out of balance. It just overheat. Actually, I have planned to show you a little bit small demo. I have a phone connected here, and the ray tracing demo I just show you. Oops. Locking, unlocking. So this one, the ray tracing demo I just show you, this is very graphic intensive. It's like it eats the GPU power for maximum. And Xcode has quite a tool for analyzing GPU. And it shows currently that it takes about 35 milliseconds on the GPU to render this picture. And you can see that frame rate is quite good in the green zone currently. This CPU actually also working. This picture is purely rendered on the GPU, but I also added some CPU code to make it like real life, more like real life. So CPU is actually also working, and one core is fully loaded. One thread is almost 100%. Like half of the CPU is working constantly. And as you may see, my point was also about horror of tools. You see that CPU here, it doesn't show any milliseconds here, but it actually also takes about 30 milliseconds. This is probably a bug in the tool. So all the tools, even the Apple tools for their phones, is considered to be one of the best. Still, it has a bug. It doesn't show me the milliseconds for the CPU. So I will leave it like this, working in for some time, 30 frames per second, and then we will see what the frame rate will be in the end of representation. So, diversity, of course. We have hundreds of different chipsets for tens of different vendors, and of course each phone vendor buys chipsets from different vendors and combines them the way he wants. So we have thousands or maybe million different combinations of CPU, GPU, and memory, and this makes there is not so big a problem for iPhone because we have limited number of iPhones. But for Android and Windows Phone, this is a true horror. There are a lot of phone vendors which, especially from China, some unknown brands which are popular. Some of them are quite popular, but vendors, they go for the spec wars and they put the biggest, cheapest number of specs chip inside their phones without thinking how they are compatible with each other. And we have sometimes very inadequate configurations. Some very powerful CPU with very weak GPU or vice versa, or both very powerful, but you cannot use this power because you don't have enough of memory under them. Big problem. And you just cannot test all of them, and You just cannot think of all variant. You just have to be cool with the thought that your game would or application wouldn't work on all configurations available. Okay, now let's talk about fixing these problems. Bright future of API. This was the Vulkan I mentioned before. So all the problems I mentioned before about the API, I'm not the only one who is aware about all these problems. Developers are struggling for ages to fix it somehow. And recently, like last year, new standards were announced. The main one is open, is Vulkan, is a replacement for OpenGL. And of course, spec wars, again spec wars. We have Apple announcing their Metal API, which is similar but not the same. And Microsoft announced DirectX 12, which is not compatible with the previous one, but they keep the name, they just increase the number, but actually totally different API. So what's fixed in those APIs? They have no global state anymore. When you're working with driver through these APIs, you use some object which is isolated. So you can make each CPU core working with separate objects and send commands to GPU separately. Very cool. Now we will have all threads or all cores of the CPU utilized. Memory management. Now you can, using this Vulkan API at least, you can ask from the device whether their memories are on the same chip or different chips. Or if they are on the same chip, you don't have to copy data from there to there. You just have to use a pointer, just point where it is already on the CPU memory. Which allows actually to make much better post effects, for example. Before currently, it is a big problem to make a post effect in a video game because you need to make a GPU render the whole picture of your game, store it in the GPU memory, then copy it to CPU memory, combine a new draw call from the CPU and say like, come on GPU, this is now my texture, now you have to apply some effect to it. And then it's copied back in the same way, which is like copying here and there actually without changing 2 times for every post effect. And you can do with new memory management without any copying. So same API for mobile and desktop. Before we had, for example, OpenGL ES, which is for embedded devices, and OpenGL for desktop and some consoles. Now we have the same API. API wars I already mentioned, that we will have 3 APIs at least. Some say that those new APIs are too complex. There are too many things you can do with those. And you're actually using new API, you can burn your GPU if you're not using it properly. But there is a counter-argument that nowadays, very rarely someone writes a pure API code for graphics. Everyone uses some kind of graphics engine, like I use Unity, for example. Or some bigger companies, they write their own engines. So some low-level guys, they deal with API, only small group of people, and others do already with using their own proprietary API. And the last one is hidden here, it's this WebGL. WebGL announced that they are not going to use Vulkan, they will stay with OpenGL. Probably there is a good reason for this, because web graphics is still not so popular. You need to do some minor things in the web browser, so simpler API maybe makes more sense. Better tools. We will have better tools in the future for mobile profiling. Probably not. I think so. We will still have this problem that we will have a lot of vendors, a lot of different GPUs, and the tools poor quality. But you can make your own tools. For example, what I'm trying to use at my work, I'm using Chrome feature, which is called Chrome tracing. I know, maybe you heard about it, probably not. I will show it to you anyway. If you write in Chrome tracing, this is actually a part of GPU profiler which Chrome uses for profiling WebGL. But it has a nice feature. It can save and load data from file. For example, I have a file stored here. This one, trace demo. And it displays it nicely with all the zooms and so on. So what, as a game developer, I can do? I just have to write in my applications, I have to write a code which will output JSON information about some milliseconds, about frame rate, into the JSON file in a specially formatted. If the format is open, you can go to the Chrome help page, and there will be specifically written how you can combine this JSON file and view this data using Chrome. So you don't have to write your own GUI tool to display the data. So it's quite convenient. You don't have to, for every gaming engine don't have to write their own some display for the profiler. Just use Chrome. Overheating. This is like a workaround. It's actually basically like the approach that we decided to use in our projects. We know that phones will overheat in some time. We know that we cannot use 100% of the resources of the phone because it will overheat too fast. But we know the average gaming session of our players. And for our current game I'm working on is like 15 minutes is the average gaming session. So we decided that we will make a graphics at the level that it will be consistent 30 frames per second during 15 minutes. If player plays a little bit longer using his device, the frame rate will drop. But it is like a balance between the visual quality, because we can lower the visual quality and increase the play session with a consistent frame rate, or we can make a play session shorter with a better quality. So 15 minutes is like for us like it's workaround. So we are testing our devices. They wouldn't overheat for 15 minutes. And we're using about 60% of device hardware capabilities. So yeah, if we use it for 100%, probably it will take 5 minutes to overheat. And again, I already told that if the vendor would put a little bit lower specs chipset into his phone and mobile device, we could make a better graphics from it actually. Diversity. This doesn't have like a good for everyone solution. How do we approach this problem? First idea which comes to mind to make graphics settings configurable in your game, in your application. So if a user opens a game and it sees like its frame rate not good enough, going to graphics settings and a little bit lowering some anti-aliasing, lowering some special effects. This is what gamers do when they play on the PC, right? Or gamers. Yeah, you go to graphics settings and tweak it. But it came out that mobile users, they don't know how to tweak it. They're not as geeky as PC gamers. They don't want to tweak any graphics settings. They just want to open a game and play it with good frame rate. So manual graphics settings is a bad idea. So we make like automatic graphics settings. We have about some projects, 3 or 4 different levels of graphics settings, and we test different devices with different settings and choose. Inside the game we have a table of devices. For iOS we use the model of the device, and for Android we use a model of a GPU chip to detect which settings to apply. We know that it doesn't work all the time. For example, we apply some settings and it doesn't work on some particular a Chinese-made device which has low memory or something like this. But it's the best solution we have till now. And as far as I know, mostly developers use a similar solution. You can never satisfy everyone. And in conclusion, mobile devices were never made for games. Though actually the number of games for mobile devices, I think, is already more than a number of games for PCs. Like there are just huge amount of games. But the mobile devices will never be made for games. For example, if you're a mobile phone producer like Samsung, gaming on your mobile phones will be somewhere in the bottom of the list of requirements for the mobile device. So they all try to make their mobile devices that they will be usable as like web browsing or mail reading, and sometimes a little bit of gaming. So these problems which we have, the devices overheating and so on, the mobile phone producers don't care about them so much, unfortunately. We will have some improvements in this field, but the solution that there will not be like a very good solution. Blah blah blah. Yep. As a mobile phone game developer, I find these problems challenging and fun. This is actually where I get fun from at work. All these devices I have, like on my table, I have like sometimes tens or even 100 devices laying around. I spend days trying one device, another device, oh, this one just crashed, this one overheated, and so on. It's a fun work in some sense. And if you want to play games, don't play it on mobile phones. Play on the PC. It's better. And this is the end. Let's check out what happened to our frame rate. So it's still running. Still running. It's a little bit dropping. You see, we had consistent 30 frames per second. Now we have 25. Okay, a little bit went back to the green zone. So it went a little bit down. And while it will be running more, it will get down and down and down even more. So yeah, maybe about 15 to 20 minutes passed, and it's time to end the gaming session. So yeah, read my blog, add me on LinkedIn, check out my Twitter. Thanks.